In class today, we learned how to simplify radicals and to apply the Pythagorean theorem. So we're going to simplify radicals, multiply them, and then we'll use the Pythagorean theorem to find the missing side of a triangle. Okay, so square root for any real numbers a and b, if b squared equals a, then b is the square root of a. We use this a lot today in our warm-ups. I gave them questions like x squared equals, say, 36. And so what we did here is we said to solve for x, you have to take the square root or do the opposite of squaring. When we take the square root here, this will give us x, and the square root of 36 is 6. We even talked about if we worked backwards and took 6 squared, we would get 36. But then we said, hey, if we take negative 6 and square it, we get a positive 36. So to incorporate both those possible answers here, we said that it's plus or minus 6. And that will occur when you have an equation. If it's not an equation, then we don't worry about that plus or minus in front of that value. So we have perfect squares, 4, 9, 16, 25. You'll notice what it takes to become a perfect square. 4 is 2 times 2. 9 is 3 times 3, 16 is 4 times 4, and 25 is 5 times 5. So you can see right here that anytime you can break a number down so that it's multiplied by the same number, that's how you'll get a perfect square. And then we listed off a bunch of perfect squares like 81, 100, 121, 144. So there are lots of different perfect squares. Simplifying radicals. To do this, we're going to look for perfect squares. If you have a perfect square under a radical, then we'll get the number 5. If we don't have a perfect square, then we're going to break down the number, and that's known as factoring. And I believe you guys talked about it back in like 6th grade as the trees. So we're going to look to do the prime factorization. Prime numbers are numbers that can be factored down to only 1 and itself. So for example, 3 is a prime number because the only two numbers that multiply to be 3 is 1 and 3. 5 is a prime number because 5 breaks down to only 1 and 5. 7 is a prime number. We could continue listing prime numbers. But we want to break down our radical until we get to prime numbers and perfect squares, or to the prime factorization. And I can show both of those processes. So here on example 1, we're going to simplify each radical. So I would start by saying, hey, what does 50 break down to? There's several ways to break this down. We can say it's 5 times 10. And then to do the prime factorization, 5 is already prime, but 10 is not. 10 is 2 times 5. And because this is a square root, remember that if there isn't a number here in the index area, then it's automatically a 2. And so what this tells you is that you are looking for 2 of the same number to bring it out of the radical. So because we have 2 5s, I'm going to cross them out and bring 1 outside the radical. 2, there's only one of them, so it will stay inside the radical. So that's how to do that using the prime factorization. Now the other method that we could do is we could break it down into perfect squares and prime numbers. So 2 times 25 gives us 50. 2 is already prime. 25 is a perfect square. So if we take the square root of 25, we get 5. This 2 would then stay inside the radical, and we get the same answer as we did before. So whether you want to do the prime factorization or prime numbers and perfect squares, you should be able to come to the same answer. So we go on to B. We have the square root of 45. We're going to break that down. 5 times 9. Now, if you recognize that 9 is a perfect square, then you can simplify that from there. If not, then we can break down 9 to its prime factorization. We have 3 and 3. And there you recognize that there are 2 3's. It's going to take 2 3's to bring 1 outside the radical, and then the 5 is all alone, so it stays in the radical. On 98, we break that down, 2 and 49. Again, if you recognize that's a prime factorization, then you can go, or not prime factorization, a perfect square, then you can take the square root of that number. Or we can continue to write the prime factorizations. 49 is 7 times 7. And here we have 2 7s, so we can take a 7 out, and then the 2 will be left alone. Now, I had 3 cases here where I didn't have multiples of anything, so I want to show you something really quick. If you were able to get the prime factorization and it came down to like 2 and 2 and 3 times, say 5 times 3 times 2, then if you have multiple numbers in there, we want to look at them. First of all, you can see we have 2 2s, so it takes 2 to bring 1 out if this were all under a radical. Then we have 2 3s. So we would take those out, and because there's already a 2 out here, we multiply whatever we bring out of the radical. And then we have this 5 and this 2. They are not listed twice, so they would be left alone in the radical. And then from here, to simplify that, you would multiply the 2 and the 3 to get 6, and the 5 and 2 to get 10, and then that would be simplified. And all of these, I think I had one more, are known as simplified radical form. We talked about in some of our classes about the significance, or when it might be really important to have an exact answer. This is an exact answer. If we were to just throw this number in our calculator and get an irrational decimal, most of the time we approximate those irrational decimals. And so we talked about circumstances that we might actually try to find an exact answer like this one here, or actually use our calculator to approximate something, and when that would be appropriate to use that answer as well. Okay, on example 2, we're going to simplify the radical. I have right here multiply the insides, multiply the outsides. So what that means is we're going to look for the numbers outside the radical. On A, we don't have any numbers outside the radical, so we don't have to worry about that. But inside the radical, or under the radical, we have this 5 and the 15. So we're going to go ahead and multiply those. But because we're eventually going to do this, I'm not going to multiply them through, but eventually we want to break that down. So I'm going to take this 15 and say, hey, that breaks down to 3 and 5. And then I'm going to look at my radical. I can see that I have 2 5s, so I bring 1 out and leave the 3 in, and that's simplified. On B, we do have numbers on the outside. I've got this 2 and this -6, so I'm going to multiply those to get -12, and then I'm going to multiply the radicals, and I have a 7, and then I have that 14, which I'm going to break down to 2 and 7. Then I'm going to recognize that I have 2 7s, so I can bring that out. I already have a 12, so I'm going to multiply that 7 when I bring it out of the radical and leave the 2 in the radical. And then I'm going to multiply the -12 and 7 to get -84 root 2. Okay, on the last one, we talked about this being a power, and because it's a power and everything inside the parenthesis is multiplied, then we can just distribute our power to both values. So we distribute it to the 3 and we get 3 squared, and then we distribute it to the 6 and we get the square root of 6 squared. And the first one's easy. 3 squared is 9, and then we talked about this in several different ways. First of all, we said if you square a square root, those are opposite operations, so they will end up canceling each other, and so we end up with just a 6. Or another way to look at it is we have 6 squared, which is 2 6s, so it takes 2 to bring 1, in this case, out of that radical. So in the end, we're left with 9 times 6, which is 54. Okay, a right triangle is defined as a triangle that has one right angle, and we talked about a right angle measures 90 degrees, and the other 2 angles are complementary. And then we also said, here's another vocabulary word, complementary means that they are 2 angles or more than 2, but in this case it will only be 2 angles that add to be 90 degrees. So then all together, all 3 of our angles will add to be 180 degrees, and that's how you know you have a triangle. The hypotenuse of a right triangle is the longest side. And I always say we got to look for the longest side or look for the side that's opposite the right angle. So here we can see this is obviously the hypotenuse. It's opposite that right angle. To be opposite, it's not going to touch that angle or form that angle. The other two sides of a right triangle we call legs. They form the right angle. And here we're going to call them A and B. It doesn't really matter what we call them, but it's going to help us when we use the Pythagorean theorem. So the Pythagorean theorem is a proven rule. It describes the relationship between the lengths of the legs and the hypotenuse of any triangle, if the triangle is a right triangle. So we have to have a right triangle. Then we get this formula, a squared plus b squared equals c squared. And we sang it to We Will Rock You, and I'll sing it really quickly. A squared plus b squared equals c squared, so that we can remember that formula. Now, the only time we can use this is if we have a right triangle. So here we're given right triangles. They're labeled as right triangles. We're going to use the Pythagorean theorem to find the missing side. So what you want to identify first is the missing side and what side it is. This is our missing side. We can see it's opposite the right angle. It's also clearly the longest side. So we're going to label it C. You could label it X, you could label it W, whatever you wanted to label it, but I'm going to use C because it fits nicely into our formula. And then we'll use our a squared plus b squared equals c squared. So I'm going to take 12 squared plus 9 squared. Those are interchangeable. It doesn't matter which one comes first. Equals c squared. Then we take 12 squared is 144 plus 9 squared is 81 equals c squared. And then we add that 144 and the 81 to get 225. And then here it asks us to find c, not c squared. So we have to do the opposite operation. Instead of squaring, we're going to take the square root. And you get c here. Earlier in the lesson we talked about that you would get a plus or a minus. And 225 is a perfect square, so it gives you a 15. And then we're going to look back at our answer. If we look up here, can we have a negative length? No, so we know that this one will not work, and the only answer that will work there is actually a positive 15. And we'll add inches to incorporate our units there. So on B, as we look at this, we have a right triangle. Again, we can see that it's a right triangle. And we're going to look at the side. We have the hypotenuse. We don't have one of the legs, so I'm going to label it B. It really doesn't matter what you label that, as long as you know how it fits into the formula. So I'm going to take my 8 squared plus b squared equals c squared. In this case, it'll be 24 squared. And then we solve that. 8 squared is 64 plus b squared equals 24 squared, which is 576. And then from here you want to isolate b to get it all by itself. So to do that we subtract 64. And we get b squared equals 512. And then to do the opposite of squaring we take the square root. And on this one, I said type this into your calculator. When we typed it into our calculators we got 22 point something, I believe. It's irrational, and so if we get an irrational number, I talked about how we need to break down 512. Now, I talked about if anything's even, we know that it divides by 2. So this is 2 and 256. Then I said, hey, why not check in your calculators to see if this is a perfect square? And if it isn't, we'll continue on breaking it down, but if it is, then we can stop there. When you type the square root of 256 into your calculator, you get 16. So it is a perfect square. We would bring the 16 out and leave the 2 inside the radical, and then our units are meters. The converse reverses the order of a theorem. I think I used the example in this class that if I go to the grocery store, then I will buy apples. That's what's known as a conditional statement. A converse switches that, so I would say if I buy apples, then I will go to the grocery store. And so that's what the converse does. So with the Pythagorean theorem, it says if you have a right triangle, then a squared plus b squared equals c squared. So we're going to reverse that order for the converse, which says if the sides of a triangle have lengths a, b, and c units such that a squared plus b squared equals c squared, then the triangle is a right triangle. So that's where we get the converse. This one right here is the Pythagorean theorem, really briefly. Then our second one here, this one's our converse. You can see that our then statement becomes the if statement, and our right triangle then becomes the converse, and we switch that order. Okay, example 4 says, determine whether each triangle with sides of given lengths is a right triangle. And we talked at great length about, first of all, how do we know if we have a triangle? Because you can get 3 lengths, and no matter how you try to draw them, you're not going to be able to connect them to form a triangle. So I said there's a really fast way to determine if you can create a triangle. First, if you add 2 of the sides, it has to be greater than the third side. And this has to work for all 3 combinations. We can see that that's true, so I'm going to move on to 4 plus 7, those 2 sides. That would then have to be greater than 5. That's true. So then we're going to choose 5 and 7. That's greater than 4, so we know that we have a triangle. So I'm going to say yes. It is a triangle. Then we have to determine, because we know we have a triangle, we have to prove that it's a right triangle. To do that, we're going to use those three lengths and put them into the Pythagorean theorem. We get to assume that 7 is our hypotenuse. So we take 4 squared plus 5 squared equals 7 squared. 4 squared is 16 plus 20, or 5 squared is 25. And 7 squared is 49. When we add the 16 and 25, we get 41. And it is not equal to 49. So we have a triangle, but it is not a right triangle. Okay, so on our second one, we're going to say, again, see if it's a triangle. To see if it's a triangle, we take 2 lengths and add them together and see if they are greater than the third side. So this first one's true. I'm going to take 2 more, 48 plus 60, and see if it's greater than the 36. That's easy to see. And then I'm going to take the 36 and 60. That's obviously greater than 48. So we can see from that we have a right triangle, or not a right triangle, a triangle. So we're going to say yes, it is a triangle. Okay, next we need to determine if it's a right triangle, so we will take this 36 squared plus 48, and because 60 is the biggest one, we put it on the other side. And 60 squared is 3600. And I know that when we add 36 squared plus 48 squared, it also gives us 3600, or 3600, and we can see that those are equal, so it is a triangle, our right triangle. Alright, I hope that will help you out with your assignment. It's 7-1, Simplifying Radicals in the Pythagorean Theorem.